All right. So conversion of regular expressions from a DFA. Now, there are three methods to doing that. We have number one, the regular expression equation method. Number two, we have Arden's theorem. Number three, we have state elimination technique. Okay, now these are all important and they all work hand in hand to solving for solving a DFA to get your regular expression. So one of the most important things to note is the Arden's theorem. And let's talk about Arden's theory for a bit. What is Arden's theorem trying to do? We want to check for the equivalence of two regular expressions. That's all. Now I'm going to write Arden's theorem out. I'll write it out, Arden's theorem, and I'll prove it. It's pretty simple. It's more like encapsulation upon encapsulation, that's all. So Arden's theorem. What does it say? It says if you have two regular expressions, P and Q, such that R is equal to Q plus RP, you can notice that the R is inside and R is outside. We can have the equivalence as QP clean closure. You don't believe me? Let's prove it. R is equal to Q plus RP, right? Now, substituting R with the entire equation, we're going to have Q plus RP again, then P. Expanding that, we are going to have QP plus RP square. Expanding that again by substituting the value of R, we are going to have Q plus RP, P square. What we have then, we have Q plus QP plus QP square plus RP cube. By now you could notice that this will keep on spawning multiple copies that are a sequential order, right? So we are gonna keep having QP2, QP3, QP4, QP5, blah 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 to QPN. What does this tell us? We can simply make this a continuous series and pretend as if R is not important anymore. So what we'll do is we'll factorize out the Q. So Q empty because there's nothing here where Q was before, but then here we can have P, QP, but now since Q is factorized outside, then we can have P square plus P cube plus dot 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 dot. What does this tell us? This should remind you of the clean closure, right? So R would be equal to Q plus the clean closure of P. Proven. How do we use this in dealing with DFAs? We'll attempt a few questions, but before that, let's establish some rules. So what are the rules? Number one, the transitions. Before we get to the rules, let's talk about assumptions. We are not dealing with empty transitions. That's number one. So we shouldn't expect a transition that is labeled with an empty to have any impact here. That's not what we are trying to do. Number two, we must have only one initial state. Let's say Q naught. We shouldn't have multiple initial states. We shouldn't have like two initial states. We need one initial state. Number three, the vertices Q1, Q2, Q1, Q2 all the way to Qn exist. Number four, we have a final state. Let's say Qn is final state. So we don't do infinite stuff here. We need to have a final state. Now, we are going to have a set of equations that will come out depending on the states. One thing that is required to note, however, is that when we are dealing with the generation of regular expressions from a DFA, the most important thing, the symbol or the state that must receive the eliminations, like the conclusions, must end on the final states. Meaning, you would be wrong if you substitute and you eliminate every other state, including the final state, and then one measly or useless state happens to be the key that you have to generating your regular expression. That's wrong. Qn has to be the final state, and the final state is the state where all your equations should combine. You should have everything combining at your final state, and then from there we translate it into the regular expressions. This might seem confusing, but I'll explain with two examples, and then we'll call it a day. So example one. Let's say we have a diagram where this is the start label, and the start state is also the accepting state. Then we have three more states: Q2, Q3, Q4, where Q2 transits to Q1 on B, Q1 transits to Q2 on A, Q3 transits to Q3 on A, Q3 transits to Q1 on A, and Q1 transits to Q3 on B. Q3 transits to Q4 on B, Q4 loops in itself on A and B, and Q2 transits to Q4 on B. Note that Q4 is a dead state, and the general rule of thumb is ignore the dead bros. These are the trap parts. You'll notice that why this is a dead state is because there is no transition outside of Q4. It's just receiving. So this is basically a dustbin or trash can. Ignoring all that, moving on, we are going to have to draw the regular expression. We are going to have to write out the regular expression equation now. So now we are going to write out all the states: Q1, Q2, Q3, Q4. Then we are going to take note of every state that transitions into that state. Now Q1 receives Q3 on A, right? So Q3 on A, plus it receives a Q2 on B. That means it transits. So, and this plus is not an addition, it's an or union in this case. Now Q2 on B q2 on B, plus an empty. This guy is not carrying any label, so it's an empty, and it's important because it signifies the start. It's because it's the initial, that's why it's having this. But notice also the the accepting state. So this is our key ingredient. This is what we will use to generate our regular expression. But then note for q2 receives transitions from q1 on A. That's all. q3 receives transitions from q1 on B, and q4 receives transitions from q2 on A, q3 on B, plus q4 on A, plus q4 on B. What we need to know is q4 is not going to help us. It's not the accepting state, and it has so many elements. So to substitute into q4 will be to shoot yourself in the foot with a shotgun. So ignoring q4, we are going to focus on q2, q3, and q1. What do we do from here? We have the equations written out. This is where we begin the state elimination method or state elimination technique, where we substitute. Let's label this equation 1, equation 2, equation 3. I'll ignore equation 4 for now. There's no need for this. So substituting equation 2 to equation 1, what we have, q1 receives that, so we are going to have q3 on A plus q1 on A B plus the empty. Expanding that, we are going to have q3 on A plus q1 on AB plus the empty. Then substituting, let's call this 4. Substituting equation 3 to equation 1, we are going to have q1 on B with A outside, q1 AB plus the empty. Expanding that, we are going to have q1 on BA plus q1 AB plus this. There's something in common here. We can factorize that out. So we are going to have q1 on BA plus AB plus the empty. From here, remember, we call Arden's theorem. R is equal to Q plus RP is equal to Q, the clean closure of P, where Q1 is equal to R, the empty is equal to Q, and P is equal to BA plus AB. What we have then, we are going to have Q1 is equal to the empty, then BA plus AB star. Now the empty doesn't mean anything, so we can also have BA plus AB star. That's all for, this is the regular expression for the DFA, this guy. Note that because this is an OR operator, the reverse can also be true. The arrangements for unions are not forced, but concatenations must be arranged properly, otherwise there will be problems. We'll look at one more question and we'll call it a day. Let's say we have another regular another DFA. We have another DFA such that it starts on Q1, it loops on itself on 0, goes to Q2 on 1, then Q2 loops on itself on 1. It also goes, then there's a state Q3, which goes to Q1 on 0 and goes all the way to Q2 on 1, and q2 goes back to q3 on 0. Writing out the state, the regular expression equation, we are going to have q1, which receives q1 on 0, or q3 on 0, or empty. Then q2, which receives q1 on 0, q2 on 1, or q3 on 1. Now q3 only receives q2 on 0. Let's label this 1, 2, and 3. Let's make that sacred. So what do? You'll notice that there's something in common. Air is also here, and this can go here, right? That's me. So substituting 3 to 2. Note that we are just trying to make this easier because there's a pattern here. We cannot work on this guy only. This guy might have what we want, but this guy is our ultimate goal. So recognize, try things out. I recommend using a pencil and just play around with what will work or what will not work. Don't just assume that what you are doing is the right thing. You are just testing out for the best routes to do this thing. So substituting 3 to 2, we are going to have q2 is equal to q1 on 0 plus q2 on 1 plus q2 on 0 with a 1 outside. Expanding that, q1 on 0 plus q2 on 1 plus q2 on 0, 1. There's something in common here. We are going to have q1 on 0 plus factorizing out q2, we have 1 plus 0, 1. By now, you should have noticed the Arden's theorem, R is equal to Q plus RP, right? Where Q2 is R, Q1 on 0. Q1 is on 1, not on 0. Q1 is on 1. Q1 is on 1, not on 0. So, correct that. Q1 is on 1, not on 0. Q1 on 1. Moving on. Substituting the value, because we know what this, we can already tell by the equivalence what should happen. So Q2, we are removing Q2 out now because R doesn't exist in this. So what is Q? Q1 on 1 is Q. Now what is P? P is this guy over here. So we are going to have 1 plus 0, 1. Clean closure. Yeah, so we have this. That's not the end, because how do we put that into the final equation, which is Q1? We can't, but we can put it into Q3. So let's call this equation 4. Now substituting equation 4 to equation 3, what do we have? We're going to have Q3 is now factoring, putting Q2 into Q3. We're going to have Q1 1, 1 plus 0, 1, or 0, 1 rather. The clean closure of that, all with a 0 outside. So if we open that, we are going to have Q1 1, 1 plus 0, 1 star, then a 0 again. Now we can put this into the final equation, which is equation 1, right? So substituting, let's say equation 5 to 1, what are we going to have? Q1 will be equal to Q1 on 0 plus Q1 on 1 plus 0, 1 star 0 with a 0 outside again plus the empty. Now Q1 on 1, Q1 would be Q1 on 0 plus, expanding that, we have Q1 1 plus 0, 1 star then 0, 0 plus the empty string. Factorizing that, we're going to have Q1 on 0 plus 1 into the bracket 1 plus 0, 1 star 0, 0 on empty. Again, we can recognize the Arden's theorem, where R is equal to Q plus RP equals to QP, where Q1 is equal to R, E is equal to Q, and the 0 plus 1 blah blah blah, blah is equal to P. So factoring that in, we're going to have Q1 would be that. Let me clean up some space. Would be that. Then we'll have this guy, 0 plus 1, 1 plus 0, 1 star 0, 0, or the clean closure of that. And since this doesn't really mean anything, we can just simply have 0 plus 1, 1 plus 0, 1 star 0, 0 star. This is the answer to that question. It will take a lot of practice to get the hang of it, but I sure hope this helped. Stay tuned for more videos. Bye.